So we're going to go over a few things from chapter 16, which is specifically about waves. A wave is a vibrational shaking motion in some kind of elastic or deformable medium that carries energy. That's really the purpose of a wave, to carry energy. And there are two broad types of waves. First type we call transverse. A transverse wave is the one that you're used to seeing. When you think about a wave, you usually think about the transverse wave. The transverse wave goes up and down. If we were going to draw a transverse wave, we could draw a cosine function or a sine function, and that would look like a transverse wave. So it kind of oscillates up and down and up and down and up and down. Okay, that's our transverse wave. The second type of wave is something called a longitudinal wave. A longitudinal wave kind of vibrates from side to side. We'll see a demonstration of this in class with a slinky, but it's side-to-side motion. It's also known as a compression wave, and it moves side to side. So with a longitudinal wave, your wave is kind of spread out, and then it kind of gets compressed at certain spots, and then it spreads out a little bit, and it gets compressed at certain spots, and then spreads out and gets compressed. So there's kind of an up and down motion here that's not to represent the same thing as in the transverse wave. It's just to show that certain areas are spread out and certain areas are compressed. So there's a little pulse, this area of compression travels down the wave shape. And we'll see this with the slinky in class. So the two types of waves, transverse is up and down, and longitudinal is side to side. So in discussing waves, we need to be familiar with a little bit of terminology. So I've driven a transverse wave here, the up and down shape, and we can label some parts of this wave. We can label the top of the wave. We typically call that a wave crest. We can also label the bottom of a wave. The bottom of a wave we typically call a wave trough. And we can label how long a wave is. So typically I start my wave up at the top point, I go down to the bottom and back up to the top where I started, and that distance from the top to the bottom back up to the top is something we call lambda, which stands for wavelength. And that just tells you how long your wave is. So as we mentioned at the beginning of this lecture, the purpose of a wave is to carry energy. In order to carry energy, they have to travel, and we can denote how fast they travel by their velocity. The velocity of a wave is going to be equal to its wavelength, how long the wave is, divided by something called a period. And the period is the same as the period that we've been studying already. It's how long it takes a wave to repeat itself. The period we denote with the letter T. So the way I think about this is going to the beach and you're standing in the waves, you count how many waves pass you in a given second, and that gives you the period of that wave. And the period is related to the frequency. Period is equal to 1 divided by the frequency. We know this from the simple harmonic oscillator. It's the same period as it was before. So we can kind of play with this and plug in for our period in terms of frequency in our velocity equation. So we got velocity is equal to the wavelength divided by the period, which is 1 divided by the frequency. I don't like having fractions inside of fractions, so when you're dividing by a fraction, you multiply by the reciprocal. So I get that my velocity is my wavelength times my frequency. And a very quick, easy way to remember this equation, which is very useful, and we should know this equation, is to look at the units. The units of velocity have to be equal to meters over seconds. So the units of velocity are equal to the units of wavelength times the units of frequency. The units of wavelength are meters, the units of frequency are hertz, which are 1 over seconds. So I get my units to work out. The units of velocity are the units of wavelength times the units of frequency, which are meters per second, and everything works. So we really need to learn and understand this equation. Velocity of a wave is wavelength times frequency. So as we talk about waves, there's a special case of something called a harmonic wave, which is a wave that repeats. So this would be like an ocean wave, a wave that never stops, as opposed to, say, sending a single pulse down a string. You'll get some experience with this in your lab, but the harmonic wave we can describe with the equation y is equal to a times cosine of kx, where this time k is not the spring constant that we're used to. K is something called the wave number, and it's equal to 2 pi divided by the wavelength. Now, if the harmonic wave, if your wave is actually traveling, it's moving, then your y changes a little bit. Your equation for your wave becomes y equals a times cosine of k multiplied by x minus velocity of the wave times the time. Or y can be equal to a times cosine of k times x plus velocity times time. And the important part of these equations are these signs, this negative and this positive. If you have a negative here, then that means your wave is traveling in the positive direction. And if we have a positive sign, then our wave is traveling in the negative direction. And again, we determine this based entirely on the sign of this v times t in our wave equation. If it's negative, we're going in the positive direction. If it's positive, we're going in the negative direction. We can do some fiddling around with our equation. Let's say we have a wave traveling in the positive x direction. We have y is equal to a times cosine of k times x minus vt. And usually when we're talking about waves, when we've been talking about waves so far, we've used something different than v. We've been worried more about omega, the angular frequency. And omega, we know, is equal to 2 times pi times the frequency. But the frequency is 1 over the period. So we have 2 times pi times 1 over the period. And if we keep working with the equations we've already found, we know that 1 over period is 2 times pi times the velocity divided by the wavelength. But if we remember, and we look back in our notes, we could see 2 pi divided by lambda is equal to k, which is our wave number. So omega is equal to k times v. And what I can do is I can distribute my equation for my y. So I'm just going to rewrite this equation, do a little bit of algebra on it, and find that y is equal to a times cosine of kx minus k times v times t. So all I've done is I've distributed that k to my x and distributed the k into my vt. And from this work that I've done above, just manipulating the equations that we already know, that we've already worked with, I can plug that in. Y is equal to a times cosine of kx minus kv, and this kv is just equal to omega times my time, times my t. So this gives us a general equation for any kind of harmonic wave. Y equals cosine of kx minus omega t. And this general wave equation, this general format, y equals a cosine kx minus omega t is very, very useful because you can represent any wave as a combination of cosines. Represent any wave shape that you see. As a combination of cosines. So I can change the amplitude, I can change the wave number k, I can change the frequency omega. And by doing that, I can represent any wave as a combo of these kinds of cosines, of this general wave equation shape. So this is very useful and has been very valuable for medical imaging. So let's say you're looking at a patient and you see their heartbeat, their heart rhythm is kind of going like a crazy wave, and you want to figure out what's going on with this. You can represent their heartbeat, this very strange looking wave shape, all these mixed in frequencies, as a combination of just cosine waves, of waves that you know how to work with, of these basic structures. And this process of representing a wave as a combination of cosines is something called Fourier's theorem. This technique is called Fourier analysis and is very, very popular and very well used in medical imaging. So if you ever need to take a medical imaging course as part of your medical training, you'll probably study this Fourier analysis. This is a very important, useful equation to know. So let's do an example. Let's look at example number 11, or problem number 11 in your textbook. It tells us we have a transverse wave that travels along a stretched spring with a wave speed of 14 meters per second. So I know that this wave is traveling at 14 meters per second. A particle at a fixed location on this string oscillates up and down as follows as a function of time. They give us this equation: y is equal to 0.02, 0 times cosine of 9.0 times t, where the displacement y is measured in meters and the time is measured in seconds. The first part, we are asked to find the amplitude. I can look at this equation and I can compare it to the general equation I have for any harmonic wave. Y is equal to a times cosine of k times x minus omega t. So for part A, I can just look and see the coefficient out front, my A, has to be equal to 0.02. So my amplitude, A, is equal to 0.02. I read that right off of the equation that they gave us. And that amplitude is going to be measured in meters because it's a height. Part B, we are asked to find the frequency of the wave. Well, the frequency is going to come in my general wave equation, not from my k times my x, but my omega times my t. Omega is my frequency, so I need to find whatever's out in front of my t to find what my omega is. In this equation, my frequency, I have a 9 out front. So my omega has to be equal to 9.0. That's going to be in omega units, radians per second. I need to get that omega into just a plain frequency. We're not asked to find the angular frequency, we want the regular frequency. So I need to remember that frequency is equal to omega over 2 pi. And you can think about this in terms of the units that you need to cancel out. Regular frequency is just 1 over seconds, is hertz. My angular frequency is radians per second. So I need to get rid of that radian. How do I get rid of a radian? I can divide by 2 pi. So I take my 9.0 radians per second and divide by my 2 pi radians, and I get that my frequency is equal to 1.43 hertz. Something that I'm going to ask everybody to do, try to remember to do from now on, is to circle your final answers. This makes things a lot more clean and a lot easier to grade for me. Part C, we're asked to find what is the wavelength of the wave. To find the wavelength, we look at the velocity of this wave, and we know velocity is equal to wavelength times the frequency. Now I know what the frequency is, I know what the velocity is, I'm given that in the very beginning of the problem, so I need to reshuffle, I need to solve this for wavelength, get wavelength by itself. So I can divide both sides by my frequency. My frequency will cancel on my right hand side, divide my left hand side by my frequency, and I find the equation for wavelength. Wavelength is equal to velocity divided by frequency. I can take my velocity of 14 meters per second. I divide by my frequency of 1.43 hertz. And I find my wavelength is equal to 9.8 meters. So the problem might have sounded complicated, sounded confusing, but it can all be solved very, very quickly, really just by knowing this general equation and correlating the pieces in this general equation with the pieces that you're given. Moving on to section 16.3. So this is all about superposition of waves. Now when waves meet each other, their total displacement has to be the sum of each individual wave. And what I've drawn here is two circumstances. First circumstance, we have a wave that goes up, comes back down, goes up, comes back down, and then reaches its 0 point again. So then we take a second wave, and it travels in more or less the exact same path. So when we have a maximum in our first wave, we have a maximum in our second wave. When we have a minimum in our first wave, we have a minimum in our second wave. So I can add these two waves together, and what I'll see is each of these waves is going to combine to kind of double my amplitude at each of the maximums and minimums. I can see I come up to a positive one for a maximum, go down to a negative one, positive one for a maximum, negative one for the minimum. My maximums reach at the same position, so these maximums, 1 plus 1, is going to add up to give me a new wave that has an amplitude of positive 2 at the top and negative 2 for the troughs, for the minimums. This specific type of combination, when your waves are adding together, when they have maximums at the same point, is called constructive interference. If your waves are constructively interfering, if the maximums reach if the waves reach their maximum at the same times, then these waves are said to be in phase. They're in sync with each other. They're in step. And this is constructive interference. Now, conversely, we can have a situation where we have a maximum of a wave number 1 and a minimum or a trough for wave number 2. So our wave number 1 goes up and goes down, goes up, goes down, and then goes back up. And our wave number 2 starts out by going down and then goes up and then down and up and back down. So we have our maximum of positive 1, our minimum, our low point of negative 1. Same thing with our second wave. But when our first wave reaches our amplitude of 0, our second wave is at an amplitude of negative 1. So we add those two together, and 1 plus negative 1 cancels each other out. So these two waves are going to cancel out and give us 0. This point, this kind of interference, this kind of combining of waves is called destructive addition, destructive interference. The waves kind of destroy each other. When this happens, when we have a wave where the maximum position of one corresponds to the minimum, the negative position of the other, this is what we call being out of phase. Now what we saw before was the two extreme cases where maximums combine with maximums and where maximums combine with the minimum in position. We can also have some kind of in-between superposition, where maybe the maximum corresponds to a halfway position for another wave. When we have this kind of in-between superposition, which you can see in figure 16.11 in your textbook, we give this a name. This is something called the beat frequency. It's something you can very well hear and understand when you're tuning musical instruments. So for any musical people, we have this concept of F beat, the beat frequency. The difference in frequencies between two waves is equal to the frequency of the first wave minus the frequency of the second wave. And this is used in tuning musical instruments. Your goal in tuning musical instruments, say you have a guitar or a violin or something, when you're tuning, you're getting this beat frequency, this offset, this interference of your waves equal to 0. So that frequency 1 maybe of your instrument and frequency 2 of your tuner is equal to 0. You want to minimize that difference. Used a lot in music. So the final section to understand in chapter 16 is all about standing waves. And a standing wave is set up when you have two waves with equal amplitude, so the same A, but they're traveling in opposite directions. We can write the equations for this. Y1 is equal to A times cosine of kx minus omega t. So that's a wave traveling in the positive x direction. So to set up a standing wave with this, I need another wave with the same amplitude, cosine of kx, but I need it to travel in the opposite direction, so I need plus omega t. Remember that negative in my first equation means I'm traveling in the positive x direction, and the positive in my second equation means I'm traveling in the negative x direction. So when I add these two together, y is equal to y1 plus y2, this is going to be what we call a standing wave. We can use some trigonometry, we can do some funny tricks, some trig identities, if we remember trigonometry at all, and we'll find that y, the standing wave, is equal to 2 times a times cosine of omega t times cosine of kx. And a couple more terminology things to note. When I have these waves traveling, and these waves cancel to 0, so this is when a crest meets a trough, I have something called a node. This would be destructive interference. This would be waves canceling. Conversely, when I have two waves combining to maximum effect, I get something called an antinode. So this would be when a crest meets a crest or a trough meets a trough. This is waves combining to their maximum amount. So to understand this, we'll need to look at a little example. We'll need to think about a practical case where we do this kind of thing every day. And one place where we see this every day is with a guitar string. So let's imagine I have a guitar and I have my string that's fixed at endpoints. Endpoint number 1 and endpoint number 2. This guitar string has a specific length. We'll call that length L. Now I can pluck this guitar string, and that'll set up waves inside of on my string. Those waves correspond to the frequencies that my guitar emits, the sounds that I hear from my guitar. Now I need the correct frequency to get a wave to fit onto these guitar strings. And what I find is that when I'm between endpoints, when I'm at my endpoints, to get a nice wave, a nice sound out of my guitar string, these endpoints have to be very, very specific. They have to reach a minimum. I have to have nodes at my endpoints of a string connected on both sides. You'll see this in your lab when you do a lab demonstration. You'll see that nodes actually happen at endpoints. So for my guitar string, I need a node. If I pluck it and I want to hear a good sound, then the first little node that I can set up, the first little frequency, first sound that I can hear off of my guitar will happen when I have a wave that goes up and comes back down, and then it bounces back, and that bounce back is going to be my standing wave. And this is what my first guitar string pluck looks like. My string is still a length L. There's still a length L separating this. But the wave that I've set up is very specific. If I look at this wave, it's not an entire wave. I have my wave goes up, comes down, but then it doesn't go back down and come back up. I can extend this so that I can imagine what the wave would look like if I was drawing a whole wave. I don't quite have a whole wave on this string. I actually only have 1/2 of a wave. So we call this the fundamental mode. It's the first guitar pluck that results in a nice node at both endpoints and actually gives me a sound. This fundamental mode is a length L, and that length is equal to 1/2 of the wavelength that can fit on that string. And what I can do with this is I can figure out what does this mean in terms of my wavelength and in terms of my frequency. If this is a guitar string, I want to know what frequency this creates. What sound do I actually hear from this? I know that frequency is equal to velocity over wavelength. So I can shuffle this equation around, solve it for wavelength, and find that wavelength is equal to velocity over frequency. So the length, equal to 1/2 of a wavelength that I can fit on my string, is equal to 1/2 of the velocity that my wave is going at divided by my frequency. And for a guitar, this velocity is very specific. A guitar creates a sound that we can hear. So the velocity that I'm talking about here is the velocity of sound, how fast sound goes, which is right around 341 meters per second. And that is the first fundamental mode that I can set up on my guitar string because I need to have nodes at both ends. So what does the second mode look like? So the second harmonic, or the very first mode after the fundamental mode, I still need nodes at my endpoints. If I want to set up a wave, I can go up, I can come back down. And that's my first fundamental mode, but I'm trying to fit my first mode in here. I'm trying to fit the second harmonic after that. So I have to come back down and come back up to my 0 point. And then this wave is going to reflect and come back. So I've set up another wave inside of this. I have my nodes at my ends again, and I can look at this and figure out how long this is. The length of this string is still L, and how many wavelengths have I fit inside of this length? I go up, I go down, I come back up. That is one full wavelength, so I have an L equal to lambda. This is going to be called my first mode. If L is equal to lambda, I can solve this for frequency. I can figure out what frequency I'm getting out of this. L is equal to V divided by F, because lambda is equal to V over F. So I can shuffle this around. I can solve for what frequency, what sound I would actually hear from this guitar. My frequency is going to be equal to the speed of sound divided by the length of the string. And I can keep going. I can draw the next mode. The next mode is going to be L equal to 3/2 of lambda, or lambda equal to 2/3 L, however we want to think about it, or frequency equal to 3 times V divided by 2L. All of these are equivalent ways to discuss the frequencies that you can set up on this string, the ways that you can make this string vibrate naturally. And each of these modes, each of these frequencies that you can make your string vibrate at to get a nice sound out, are called eigenfrequencies. This concept of eigenvalues, eigenfrequencies, we should be familiar with this from any kind of matrix math that you've done in the past. So let's take a closer look at these frequencies, these ways that we can make our string vibrate so we get a nice sound out. The fundamental mode, we'll call it the 0th mode. We have L is equal to 1/2 of lambda. The first mode, L is equal to, we'll call it 2/2 lambda. The second mode, L is equal to 3/2 of lambda. So you can keep seeing a pattern here where the third mode, L, will be equal to 4/2 of lambda. And then 5/2 of lambda. And so on and so forth. So we have a general format that we can use. The n-1th mode is going to give us L is equal to n over 2 times lambda. This is a general equation that will work to find any mode for a situation where we have nodes at both ends. So this is a case where we have a guitar string attached at both ends. And in class, we're going to see an example. In class, what we have to look forward to is talking about this a little bit more, a little bit about what these frequencies are, and what we're going to see is what happens when you help any one of these harmonic frequencies, if you kind of increase them, if you encourage them. It's called a driving frequency. So if you drive one of these frequencies, encourage them to be stronger, you can create something we call resonance. And this process of resonance, creating resonance, driving frequencies, encouraging harmonics, can be pretty destructive. And we'll see this in class. The destructive power of resonance.